Welcome to this NPTEL lecture on reflector antenna systems. But before going there, actually in the last lecture we have discussed about corrugated horn. That time I forgot to show you some diagrams. So, a corrugated conical horn, this is conical, but a corrugated section looks like this. In the input feeding section there is a tapered thing, and then in the radiating zone or near the aperture there is this corrugation. Now, this is the, you can say, side view, but if we look at the things, actually corrugations means this, that some portion you are removing the metals. So, this is for a planar surface, corrugation looks like this. So, on those two surfaces, on this surface these are the corrugations, that means these portions are metallic, but between portions are non-metallic. Similarly, here, so that is extending throughout the surface. So, this you please add this portion to the previous lecture. Now, today we start with the reflector antenna, So, at microwave frequencies, this is mostly used antenna, and majority of satellite links use these reflector antenna systems. The geometry of the reflector system you can see here, we are seeing it as a paraboloidal, because this is actually the conic section paraboloid, which is obtained by revolving this parabola about this axis. If this is the axis of the parabola, if you revolve it, you get the paraboloid. So, the reflector is the paraboloid. We have a feed horn at the focus of the paraboloid. So, now here please understand this dashed line, that is called a plane, because actually if you think of a dish antenna, all of you have seen. Now, think that if I take from one edge to other edge, if I take a plane, that plane for the paraboloid will be a circular disc. So, this is a plane thing, this is called aperture surface. So, actually it is a circular disc, planar disc for this paraboloid thing. So, rays that are going from this feed, if they go here, after getting reflected from the paraboloid, that becomes parallel to the axis. Similarly, here, now this diameter of this aperture is 2a, or radius is a. Now, this is an important ratio, as we will see, that this f by 2a or f by d, that is a specification for a parabola, because it determines all its radiation properties. F by d ratio people generally call it. Now, we first find out, because we will have to put our previously derived result, that if I know the aperture field distribution, that means if I know the field distribution on this aperture, I will be able to say what is the field, that we have seen by Fourier transform method, etc. So, we will have to know what is this aperture's equation, etc. Now, parabola equation we know. So, from the basic geometry, now we will derive the geometry of this thing. So, the other portions of the drawing I will come later. So, I can say that let me draw a parabola, and this is its point. Let us say the focus I am calling O, and the suppose I have an incident ray from here, that ray is coming to the focal plane, and the point where the parallel ray meets the focal plane, let me call that as point Q, and this point let me call it P, where the ray has hit. Now, from the parabola's basic, any conic section, if you remember that if from the distance from the focus to any point on the conic section, that is always a constant. If you remember, the conic section which has two focuses. So, from a point on the section, if you add those 2 points distance, focus, suppose I have a ellipse and it has 2 focus. So, this is a point. So, sum of these 2 distances is always equal to twice of the focus. So, here the same thing we can say that OP plus PQ, that is equal to twice F, a constant. Okay. Now, you can see from the geometry that this angle is theta. So, if this rays or this distance is r, then this will be r cos theta. So, I can put that r plus r cos theta is equal to 2f, or r is equal to 2f by 1 plus cos theta, or I can say this is f sec square theta by 2. So, this is this r, that means if I take the r here, then the corresponding theta I will have to say, and this equation will be satisfied. So, basically the paraboloid is a locus of this point r. Okay. Generally, the horn is placed at the primary focus as a feed. Now, here actually the analysis for that, we will assume that since this is a microwave thing, we assume that ray optics, which has a strong foundation from Maxwell's equation. Actually, Sir Jagadish Bose proved that optics also obeys Maxwell's equation. For the first time he proved it, because Maxwell did not say that explicitly, he just conjectured probably these laws which I have found, they also are valid for optics, but Sir J.C. Bose proved it. So, we will take help of ray optics at these fields, and it had been seen that those laws hold good here, because the results obtained after this fully matches with the experimental observations. So, the relevant results that I will take, that is called that locally all the waves are plane waves. Actually, in ray optics this holds good because their wavelength is very small, but here also we will assume this, that locally all the rays. So, first thing is the waves travel in a ray, that we will assume here also, actually in a tube of ray, because we have a beam. So, that is why tube of ray, and locally they behave as a plane wave and propagates in straight line along straight rays in homogeneous medium. At a boundary between medium, they are reflected or refracted at the tangent plane according to Snell's law and the Fresnel reflection coefficient holds good. The power is viewed as flowing in flux tube, and if a flux tube is reflected from a perfectly conducting surface, the power in the reflected flux tube equals that in the incident flux tube. These are all these results you know, just I am saying it, that the electric and magnetic fields are transported along the flux tubes. The electric and magnetic fields are mutually perpendicular and orthogonal to the rays, because rays are the direction of propagation. Since it is plane waves, so electric and magnetic fields are orthogonal to these. Okay. And for the paraboloid surface, all rays from focus are reflected to become parallel to axis. At the edges, the rays are diffracted, but we will neglect the effect of diffraction in this analysis. I already said that the aperture is a plane in this case, which is circular disc just in front of the surface. Now, after saying all this, my actual intention is that we have already seen the horn antenna. So, this we know the suppose we know the radiation pattern of this feed horn, but to calculate what is happening to the radiated field by the reflector, we need to find this field distribution on this aperture. So, we now relate that if I know this power radiation pattern of the feed, what will be the aperture field distribution? This will be our first task. But before that, I will want to show you two slides. Whatever I said, that reflection of a flux tube, if you have a plane reflector, then this is the incident flux tube, and then this is the reflected flux tube. What I said, this is the central ray, there are other rays, these are the two edge rays. So, you see that E and H field, they are orthogonal. So, E, H and the ray, they form a triplet, etc. So, this is plane reflector, but we do not have a plane reflector. So, we will have to see some next slide. So, our case will be like this. We are having an incident tube, then that incident tube will go here, only one ray is shown, but actually here also there will be a tube, and incident tube thing and the reflected tube total power, that should be conserved, because this we are assuming to be a conducting surface. Okay. So, with that I again go back here. Now, you see that actually you see that there are two ways by which this paraboloid reflector can be analyzed. One is the way I am saying that aperture field I will calculate, and from aperture field we know what is the far field, etc. That yesterday we in the last lectures we have derived. But there are also people can say that I can also find out at this paraboloid reflector what is the current, because this is not an aperture problem, because this is a real paraboloid conducting surface is there. So, I can find the conduction current here, and from that also I can find the thing. Both methods are there. This is called induced current method, by which wire antennas are analyzed. So, that can be done. Also, this aperture is a aperture. So, that is why here from the field we do. So, we will take the aperture field method, because it will help us to illustrate what we have derived for planar antennas, etc. So, for that let me introduce that suppose g theta phi is the power angular radiation pattern of the feed located at the focus. This is actually horn antenna. We are not saying horn because there can be other things also, but mostly in all the cases it is horn. So, g theta phi is the power angular, because I am saying it is expressed in terms of theta phi. So can I say that g theta phi by r square is the power per unit area radiated by the feed. Okay. Now, the power incident on the reflector power incident on the reflector in the flux tube of angular width d theta d phi is what? You see that I am saying that I have this. Now, this is d theta, and in the azimuthal plane there will be a d phi. So, in that tube how much power is there? That is called pi theta phi. So, that I can easily calculate because I know this. So, pi theta phi is g theta phi by r square into the area in that angular strip. And can I say that what will be that area? One will be r sin theta d theta, another will be r d phi. Okay. So, this is then got. So, actually you will see that these r will get cancelled. Now, this same power from the law of optics, this same power must appear in the reflected flux tube, and for the reflected flux tube you see that. So, suppose this d theta d phi, this power has gone here, this is that tube, incident tube. Now, while it is reflected, you see I have something like it will occupy the portion. If I call that the distance from the center, this variable is rho, this becomes a cylindrical type of thing. So, can I say that d rho d phi, that will tell me, because now no more theta is there, because this has now become a straight rays. So, in d rho d phi direction, in d rho and strip consisting of d rho d phi, it is variation of these two parameters, whatever power is there that should be equal. So, I can say that this same power must appear in the reflected flash tube of width d rho on the aperture surface. So, I can say that this should be equal to, and for that suppose it produces a power density per unit area in the aperture surface, it will produce a power density per aperture area in the unit surface, and let me call that, or let me change it, that let me call this P rho phi is the power density reflected to power density or power per unit area, let me say power per area reflected to the aperture surface within width d rho and angular spread in azimuth d phi. So, I can say that P rho phi, then rho d phi and d rho this is the total power that should be equal to that pi theta phi. So, I can say that this pi theta phi, already I have shown that it is g theta phi sin theta d theta d phi. So, let me write P rho phi and in place of this rho, to cancel out, I write rho is what? From the figure you can see it is nothing but r sin theta. So, r sin theta d rho d phi is g theta phi sin theta d theta d phi. That solved my problem. So, I can say that also since rho is equal to r sin theta, so let me simplify this first. So, this is P rho phi will be g theta phi 1 by r d theta d rho. Okay. Now, this d rho d theta needs to be evaluated. I know what is the relation between rho and theta. So, I have rho is equal to r sin theta. So, d rho d theta will be 2f. Also, r sin theta means I can put r value, I can put 2f, so that it become constant, otherwise r is a variable, but 2f sin theta by 1 plus cos theta. Now, you differentiate with respect to this, that becomes 2f by 1 plus cos theta. So, now you put it there. So, you get P rho phi ঠিক কি acha okay you need to have something 2f1 plus cos theta. Now some more algebraic manipulation. So I can say 1 plus cos theta by sin theta is 2f by rho. So you can write 1 plus cos theta whole square minus sin square theta by 1 plus cos theta whole square plus sin square theta will be 4f square minus rho square by 4f square plus rho square. Also we have that 1 by r is 1 plus cos theta plus 2f. So all that if you put, finally I can write p rho phi is g theta phi 16 f square by 4 f square plus rho square. So this is the expression I was finding out, that what is the power density at the aperture. I know g theta phi, everything else you see that is constant. So at a particular rho, if you ask me that what is the power density, putting that value I can tell you. That means at all points on the power aperture, which is a circular disc, I now know the power density. So my rho varies from 0 to a, or 0 to or you can say plus a to minus a. So I put and I get. So now I know the power distribution on the antenna. Now from here we will take certain things that you have seen that it is always better, or we have not seen that, but please note actually due to lack of time we did not do that. If an aperture is illuminated uniformly, that gives us the maximum radiation. That means the radiation is in the broadside direction and peaks. Actually from array theory concept you can see that when we uniformly illuminate the array elements, then also you get a peak. In other cases you do not get, because all are constructively added. The same thing in a distributed fashion, that if you uniformly illuminate with same phase distribution, same amplitude, then you get very peaky thing along the broadside. So that is always desirable, because that gives you maximum directivity thing. So always that is a dream. So if I want to make p theta rho phi uniform, then what is my requirement on g theta phi? From here you can see that g theta phi should be proportional to this sec 4 theta by 2. How? Just you put it, bring this angle theta, because these things actually this relation, that 1 plus cos theta by 2f actually by putting angle, or you can say that, see the other way, that g theta phi, suppose a thing, the feed is uniform, the feed giving you uniform radiation, then p rho phi will be proportional to this 16 f square by 4 pi square f square, which is nothing but 1 plus cos theta whole square. You will see that. So that is, so I will rather write, otherwise you, that if g theta phi constant, then p rho phi from this expression becomes 1 plus cos theta whole square, which is 4 cos 4th theta by 2. So, that says that the aperture is not getting uniformly illuminated. So, there is a distribution, and where is the maximum aperture field, that is obvious power, that is obviously at the theta is equal to 0. So, compared to the center, the edges of the aperture, that means here I get maximum radiation and here I get minimum radiation. So, this in reflector term people call it, there is a taper in the amplitude if we have this. Now, this is not desirable, rather the other thing is desirable. We want to have p theta phi constant. So, your g theta phi, that means the feed pattern, that should be proportional to sec 4th theta by 2. Now, what do you mean by that? G theta phi sec 4 theta by 2, that means for theta is equal to 0, that means at the central location the sec theta is 1, and for other places, that means at the edge, that is very high. Now, that is what will happen, that actually that means what we are saying, that it is having very high power in these 90-degree directions. So, and very small power in this, that means minimum here radiating, and so we will see that will give that many power will be lost, the reflector will not be able to intercept that power, that is called spillover loss. We will come later to spillover loss. So, it is not very desirable. So, that means this is optimum, but this is not desirable, and practically we cannot do that, because that will give rise to high spillover loss. So, it will definitely give us very high directivity. This choice if I make, I will get very high directivity, but the efficiencies they will kill that directivity. So, that is why we will see that this is not done. And also here I will say that what is the angle, because you see that though I can make this paraboloid reflector come to this pi by 2, but we do not do that, because then our aperture becomes very small. So, up to certain angle it is there. So, that is called angular aperture. That means, if I have a paraboloid, so this angle is called psi or psi by 2. So, this angle is also psi by 2. So, that means angular aperture of the paraboloid is psi. So, at that point, what is the value of rho? Rho is A. So, rho at extreme point or edge, at extreme point or edge of the paraboloid, rho is definitely equal to their A, and that is 2f sin psi by 2 by 1 plus cos psi by 2, the paraboloid equation. So, this is nothing but 2f tan psi by 4. So, I said that basically you see this psi is governing the whole thing. So, this thing people also sometimes this whole thing is specified by specifying the f by d, d means 2a. So, f by 2a is what? 1 by 4 cot psi by 4. So, sometimes if the angular aperture is specified, f by d ratio is specified, or if f by d ratio is specified, I can find what is the angular aperture of the paraboloid. Now, here I will say that ultimately we will see that the amplitude taper, what is the this that amplitude taper in the aperture field this reduces the directivity, because this increases the beam width, so reduces directivity. So, that is not desirable, but amplitude taper in the aperture field also decreases the side lobe level. This will show later. So, now this is the problem, this is the designer's problem, that how much amplitude taper I will have to give, because one side it reduces directivity, another side is puts the side lobe level down. Now, in a communication problem, generally this side lobe level reduction is more important. That means, if you have an interferer nearby, then you want to put a side lobe to that place. That is more important, because you are not so concerned, particularly in communication, the directivity or SNR is sufficient. So, directivity is not a concern, you can suffer a low gain also. So, that is preferred, but in radar type of applications, there the directivity is prime thing, and generally they do not consider, they do not bother about the interference from others. So, there actually this is the thing, that what is the optimum value of the taper so that I can get maximum anything. But this thing qualitatively you remember always, because this is the dilemma in which a designer always sees. So, this is important. I now that compromise is actually our whole study of engineering. Actually, the next lectures will be actually how an engineer makes that compromise between these. Okay. So, I stop it here. In the next lecture, we will see, now we have got the aperture field, we can immediately find out what is the directivity of this antenna. Thank you.